we come to what is arguably one of the most famous limits that you have learned so far. Limit x going to 0 sine x by x equal to 1. Now, to prove this, I would require some elementary properties of the trigonometric functions. Now, these can be proved directly by understanding that sine and cosine and so on can be defined using circles and triangles within circles and using theorems from geometry. I don't want to do that. I want to give a purely analytic proof, by which I mean sine, cosine, etc. I want them to be defined using analysis and their basic properties also proved using analysis. Now, I would define these trigonometric functions at a later point of time. Meanwhile, you will have to take some basic facts about trigonometric functions on faith. Of course, you have manipulated these identities quite a bit in your high school. Just take them for granted for the time being. Now, to prove that limit x going to 0 sine x by x equal to 1, I am not going to do it directly. I am just going to invoke this very useful theorem which we have already seen for sequences. Theorem squeeze or sandwich theorem. So, let f comma g comma h from a to r be functions. Suppose x is a limit point of a and limit y going to x f of x equal to limit y going to x, sorry, this should be f of y, h of y are both equal to L. Further assume that for some ball B with center at x, we have just f of x, sorry, f of y is less than or equal to g of y is less than or equal to h of y for all y in B intersect A. So within the vicinity of this point x, some small vicinity, I have a relationship between f, g and h. F is less than or equal to g is less than or equal to h. Then limit y going to x of g of y is also L. Okay, let's prove this. First proof is follows immediately from corresponding theorem for sequences. That's the first proof. Let's give another proof directly using epsilon delta. Proof 2. Fix epsilon greater than 0. Then we can find delta greater than 0 such that mod f of y minus L is less than epsilon, and simultaneously mod h of y minus L is less than epsilon whenever 0 is less than mod x minus y is less than delta. This just comes directly from the epsilon delta definition applied to f and h, then taking minimum of the two deltas. Since I have done such things quite a bit for sequences, I will not be explicitly saying anymore how exactly this delta was constructed, satisfying these two conditions simultaneously. Okay. Now, we may assume b x delta is contained in b. Why can we assume this? If not, just make delta even smaller in order to make bx delta contained in b. This can be done. Then we know that f of x is less than or equal to g of x is less than or equal to h of x. And now the proof should be very, very similar to what we did for sequences. We get f of x minus L is less than or equal to g of x minus L is less than or equal to h of x minus L. Right? This just follows by subtracting L throughout the equation. Correct? But f of x minus L is greater than minus epsilon. Right? Oh, just a moment. I have to change all these x's to y's. Sorry about that. F of y is less than g of y is less than h of y. F of y minus y is less than g of y. So f of y minus L is greater than minus epsilon, whereas h of y minus L is less than epsilon. Why? This just follows from the fact that mod f of y minus L is less than epsilon and mod h of y minus L is also less than epsilon. Right? That immediately gives minus epsilon less than or equal to g of y minus L less than or equal to epsilon, and we are done. I will not belabor the proof anymore. Okay? So this shows that the squeeze theorem is true for functional limits also. And if you notice, this proof is more or less the same as the squeeze theorem for sequences. So at this point, let me make a parenthetical remark that is sort of beyond this course. Now you might think, why do we waste time first doing sequences and proving some theorems, then doing the exact same theorems for functional limits once more, and later in the course you will see something called uniform convergence, and the same things you will do for uniform convergence also. You have various notions of convergence and you have similar theorems for all of them, and you're wondering why is it that we are not unifying all of them. They can be unified. You can give a general notion of limit using some abstract machinery. This has been done by the mathematician A.F. Bearden. Just Google A.F. Bearden limits and you will get this. This is just some extraneous things. If you are interested, you can pursue this. Okay, coming back to more pressing issues. How do we use this to show limit x going to 0 sin x by x is equal to 1? How do we do this? Well, I need to use a fact. For x close to 0, cos x is less than sin x by x is less than 1. This will be proved at a later point when I define the trigonometric functions precisely. Okay. Now because of this, notice that the right hand side is a constant function. This converges to 1 as x goes to 0, and this cos x is a continuous function. That's another fact that you know, and cos 0 is 1. Therefore by squeezing theorem we are done. Okay, so this is a short proof. Of course, all the heavy lifting has been shoved under the carpet and left for a later time, but once we do that, this is fairly straightforward. The squeeze theorem is very, very useful. Again, just as in sequences, directly using the epsilon delta definition to show that some limits are true is a very, very bad approach. You must use it as a last resort when every other things fail. First, try to apply the various limit laws, squeeze theorem, and so on, and try to get the limits. If everything fails, resort to using epsilon delta. This is a course on real analysis, and you have just watched the proof that limit x going to 0 sine x by x is 1.